This is Bob Capetta, and we are going to look at more calculus optimization problems. How we determine mins and maxes for word problems. So here's our next example. A rectangular storage container with an open top is to have a volume of 10 cubic meters. The length of the base is twice the width. Material for the base costs $10 per square meter. Materials for the sides cost $6 per square meter. Find the dimensions of the box that would minimize the total cost. And then to give you some help, I'm letting x be the width of the base and y be the height. So what do we know? The length of the base is twice the width. So if x is the width, the length is twice the width, so the length would be 2x. The height we said was y, so that's good for us to see. What do we know? We know volume, of course, is length times width times height. The length is 2x. The width we said was x. The height we said was y. So the volume of this box is 2x squared y. But what else do I know? I said the volume is 10 cubic meters. So 10 has to be 2x squared y. If that's the case, I can solve for y, dividing both sides by 2x squared to say that y is 10 divided by 2x squared. Of course, reducing that, 10 divided by 2 is 5, so y is 5 over x squared. So that's important for me. Now, we need to figure out what the cost of this box is going to be. So, the base is $10 per square meter. The sides are $6 per square meter. Remember, the length is 2x, the width is x, and the height is y. So here's our picture. Length is 2x, width is x, height is y. So there are 5 sides to this box. Here, the front piece, you'll notice this distance is x, this distance is y. So this area here would be x times y, would be the front and back of the box, would have an area of x times y. The right side, the length is 2x and the height is y. So the area of the right side and the left side would be 2xy. Now how about the bottom? You can't see the bottom, but the width is x, the length is 2x. So the area of the bottom would be x times 2x, or 2x squared. So again, 5 sides: bottom, front, back, left, right. What's my area of the bottom, which I'm calling the base? X times 2x, 2x squared. Front, x times y, but what do we say y was on the previous page? If you'll recall, we said y was 5 over x squared. So if the front is x times y, x times 5 over x squared, or 5 over x. Back, same thing. Remember, the back is just a perfect copy of the front. So the back is also equal to x times y, x times 5 over x squared, which is 5 over x. Left and right side, we can see the right side here, 2xy, 2x times 5 over x squared, 10 over x. Left is the same, also 10 over x. So we've got the area of all 5 pieces, 2x squared, 5 over x, 5 over x, 10 over x, 10 over x. But the bottom cost more. We're using a different material. So let's go back and take a look. What did the bottom cost? The base, the bottom cost $10 per square meter, but the sides each cost $6 per square meter. So $10 for each square meter here, $6 for each square meter there. That's going to go ahead and give us the total cost for each of the 5 panels. So what's that going to look like? Again, material for the base is $10 per square meter, materials for the sides, $6 per square meter. So $10 times the area, $10 per square meter times 2x squared square meters gives me 20x squared dollars is the cost of the base. The front, the area was 5 over x, but it cost $6 per square meter. 6 times 5 over x, 30 over x, same for the back. 6 times 5 over x, 30 over x. The left was 10 over x, but it also cost $6. 6 times 10 over x, 60 over x. The right, 6 times 10 over x, 60 over x. Add all these together. 30 and 30 is 60, and another 60 is 120, and another 60 is 180. 180 over x plus 20x squared will give us our total cost. And that is what we want to minimize. Our goal is to design this box so that the cost is minimal. So how do we do that? What's our strategy going to be? We're going to find a critical value by taking the first derivative, set it equal to 0, and then solving for x. So here is my cost function. C of x is 20x squared plus 180 over x, which we'll rewrite as 20x squared plus 180x to the negative 1. We need to take the first derivative, so that'll give me 40x minus 180x to the negative 2. 180x to the negative 2 is the same as 180 over x squared. That is my first derivative. But we're going to set our first derivative equal to 0 to get our critical value. So my next move is to recognize that 0 has to equal 40x minus 180 over x squared. So if that is the case, 180 over x squared would equal 40x. Multiplying both sides by x squared, we get 180 is 40x cubed. Dividing by 40, 180 over 40 is x cubed, which is 18/4, which is what, 9/2, I believe. So we get x cubed is 9/2. So x is the cube root of 9/2. Let's get a decimal approximation for that. Cube root of 9/2 is about 1.65. So to keep the computation reasonable, I'm going to go ahead and use that approximation number of 1.65. Now, do I know for sure that is minimum rather than maximum cost? What am I going to choose to do here? So there's our first derivative. There's our second derivative. 40, negative 2 times negative 180 plus 360 decreases by 1x to the negative 3. So my second derivative of x, using the second derivative test, is 40 plus 360 over x cubed. Now what is the second derivative at our critical value? Our critical value was 1.65. 40 plus 360 over 1.65 cubed. I don't really care what it is, I just care what the sign is, and it's positive. This is a positive number, that's a positive number. So the second derivative is positive. If that's the case, I know that this thing is concave up. I have a concave up situation. In a concave up situation, I know that my value, my critical value, will be a minimum. So the cost is minimized at that critical value when x is 1.65. But what is the minimum cost? How should I build that box? What are the dimensions of what I have? Well, what do we know? We know first that x is the cube root of 1.65. What is y? What did we say y was? So somewhere way back when, we did some analysis for y. So that would have been early on, once we had our volume. So you'll notice what we had. We said the volume was 10 equals 2x squared y. And from that then, we had y was 5 over x squared. So we know what y is. Y is 5 over x squared. So now we want to use that. So how are we going to use that? Y is 5 over x squared. We said x was 1.65. So y is 5 over 1.65 squared, or about 1.84. So we have x, which was our width, if you remember. We have y. Y was our height. What was the length? The length was 2x. So 2 times the width, 2 times 1.65 is about 3.30. And then our height there is 1.84. But our question was, what was the minimum cost? So what was our cost function? Cost as a function of width. Cost was 20x squared plus 180 over x. So if I replace the 1.65 in for x, I get C of 1.65 is 20 times 1.65 squared plus 180 over 1.65. What's that going to give me? A total of 163.5. Now we've shown that's a minimum with our second derivative test. So we have a minimum cost of 163.5 or $163.50 when the width is at 1.65 meters, I believe. The length is 3.30 meters and the height is 1.84 meters. And I believe I have one more question to go in this realm. Let's take a look. You wish to design a cylindrical can that has a volume of 100 cubic inches. How should you design the can so that the amount of material used is minimized? So the amount of material we have here, we have a top piece of this can, of this cylinder. We have the bottom piece of this cylinder, then we have the sides. So in essence, there's three pieces of interest. Now, the top is a circle. The area of a circle is pi r squared, so the area of the top of the can is pi r squared. Now, how about the bottom of the can? It's the same thing, right? The area of the bottom of the can is also pi r squared. So those are two of the three pieces we need. But how do I find the third piece? What do I find this lateral surface area? Well, the strategy I encourage you to do is to imagine removing the top and the bottom, slice it up a seam, and flatten it out. So what the result would be a rectangle. So try to visualize that. If you slice it up a seam and flatten it out, you have a rectangle with a circle on top and a circle on the bottom. So this kind of gives us the picture. But the key idea is to recognize that, yes, that's the height of that rectangle. But this other dimension is the circumference of the circle. Do you see that? All the way around here is the circumference of the circle. That would be the length of that rectangle if you remove the top and the bottom, slice it along a seam, and flatten it out. So 2 pi r is the circumference of a circle, 2 pi r. That's this distance. H is the height. So the area of this piece would be 2 pi r h. Now, how do we use this? How do we put this together? So this area is pi r squared, this area is pi r squared, this area is 2 pi r h. So can I put those together? The total surface area, pi r squared plus 2 pi r h, pi r squared plus pi r squared, 2 pi r squared plus 2 pi r h. That is what I want to optimize, but I have two variables. I have r and I have h. What am I going to do about this? So yes, I have surface area is 2 pi r squared plus 2 pi r h, but I want to figure out some way to get rid of h. And we do that by using our volume. So if we go back, what did we say early on? The volume of the can is 100 cubic inches. What is the volume of a cylinder? Area of the base times the height. The volume of the cylinder is pi r squared times h. So pi r squared times h would have to equal 100. That enables me to solve for that h value. So using that, and what did we say the volume of the cylinder was? It was 100. So if we want to solve for h, divide both sides by pi r squared. 100 divided by pi r squared equals h. Then I can go ahead and I can plug that back into my formula for surface area. What did we say? We said surface area was 2 pi r squared plus 2 pi r h. So we know that, and I can plug this h of 100 over pi r squared in for h here. Now, what happens? The pi's divide out. 2 times 100 is 200. R divided by r squared is an r downstairs. So what I get is surface area is 2 pi r squared plus 200 over r. And this is the function that I want to minimize. I want to design the can so I have minimum surface area. That'll give me minimum cost, likely. So instead, I'm going to let x represent the radius rather than r. I prefer to take derivatives with respect to x, just a personal preference. So changing that surface area function to f of x, 2 pi x squared plus 200 over x. Just don't forget that x is the radius in terms of my notation. So I want to minimize that function, take its first derivative, set it equal to 0, solve, and see what we get. So this is what we have. I want to use the derivative of that function, so I'm going to rewrite 200 over x as 200x to the negative 1. So f prime of x will be 4 pi x minus 200x to the negative 2. What does 200x to the negative 2 mean? That's 200 over x squared. Now I've got to set that equal to 0 and solve. That will be my critical value. Adding 200 over x squared to both sides, I get 200 over x squared equals 4 pi x. Multiplying both sides by x squared, I get 200 is 4 pi x cubed. Dividing by 4 pi, 200 over 4 is 50. 50 over pi is x cubed. So x would be the cube root of 50 over pi, another unpleasant number. Let's go ahead and use the decimal approximation here of about 2.515. Remember, x represented the radius. Now, I want to minimize the surface area. I've got to make sure that it really is a minimum. I'm going to proceed by the second derivative test to do that. So here was my first derivative, was 4 pi x minus 200x to the negative 2. What is my second derivative? 4 pi negative 200 times negative 2 plus 400x to the negative 3, which is 4 pi plus 400 over x cubed. Now look at this. No matter what x is, as long as x is positive, this result is going to be positive. So what I'm saying is f double prime now of my critical value, 2.515, is 4 pi plus 400 over 2.515 cubed, certainly bigger than 0. If it's bigger than 0, we know that we have a concave up situation. If it's concave up, the second derivative is positive, my value will be a local minimum. So what this tells me is the surface area is minimized at that critical value of 2.515. We've got a little bit of algebra to do to determine how we're going to design this can to optimal specifications. So x is the cube root of 50 over pi. Remember, x was the radius, so let's go back and use the radius notation. And you'll also remember from our volume formula, we said 100 over pi r squared equals h. Pi r squared h was the volume, and the volume was 100. So this enables us to solve for the height of the can. Plugging in the 2.515, I get height is 100 over pi times 2.515 squared, which gives me height is about 5.03, which is essentially twice the radius. So notice the height and the diameter of the can are the same. Interesting. Very close. This is a round-off error here, which is why they're not exactly the same. The diameter and the height of the can are the same to minimize the surface area. Now, what is that minimum surface area? We had this formula. We said surface area was 2 pi r squared plus 200 over r. I'm going to plug in my r here of 2.515. So I get surface area is 2 pi times 2.515 squared plus 200 over 2.515. And what do I get? What is my surface area? About 119.3 square units. I forget exactly what our units were here. But that is going to occur when the radius is about 2.515 and the height is about 5.03, giving us a minimum surface area of about 119.3 square units. And that will conclude this lesson.